Hello students, welcome to another tutorial on fluids in motion. In this video, we're going to look at the Poiseuille equation and then also look at the quantities or the variables that are involved in this equation. And later on, we're going to look at how we can use the Poiseuille equation to work out an example. Now, first thing that we're going to look at is what the equation is actually. So in the video, we're not going to derive this equation. So we just want to see the variables that are involved in this equation and how they affect the flow rate. And then after that, we also just want to see how we can use this equation. So we're not really going to look at how this equation is derived. Now, this equation is used whenever we have flow, and then we also have viscosity present. Then this equation has to be used. Now, it's kind of similar to the Bernoulli equation, but the key difference, when I say similar, of course, I mean we can use the Bernoulli equation to find the pressure drop or the pressure rise, or don't just say the change in pressure. But we can also use the Poiseuille equation to calculate the same thing. But of course, when can we use the Poiseuille equation? When we are told to say that there is viscosity. So this symbol here, eta, so this symbol is, this is a symbol we use for viscosity. So I hope you guys, you guys know this symbol by now. There was a time that we brought this, we used this symbol already. So you guys should just be familiar with this symbol. So it's not N, it is eta. So notice how we write it. So something like that. Okay. So this is viscosity. So apart from this, the other key term that I want you guys to just keep in mind. So the first thing was, when do we use this equation? Whenever you see a question mentioned to say there is viscosity. So if there's viscosity in the problem, then you know to say that you have to use the Poiseuille equation. Okay. Now, next up, this quantity here, Q. You see, Q is the flow rate, but there are two types of flow rates that you have to keep in mind. J gives you the mass flow rate. So we looked at this before, we described what it was. So this is going to be M over T, or it might be changing M over changing T. But Q, on the other hand, this is the volume flow rate. So since that is volume flow rate, we expect that it's going to be V over T. Sometimes you can write it as change in V over change in time. It's really up to you and what you prefer. It's basically the same thing. Okay. Now, when you're going through a question, you guys, it's very important to pay attention to the values that you're being given. So the question will just say the flow rate is, let's say, 4 grams per second. So you're saying this is the flow rate. So now, how do you know that this is J or it is Q? How can you tell? Well, look at the units. If you see the top unit has a unit for mass, then you know to say this is the mass flow rate. If the top part has unit for volume, then you know to say this is a volume flow rate. In this example, of course, you see that the top part has the unit, the gram. The gram is used for mass, implying that this is the mass flow rate. So we can't use this in this equation, the Poiseuille equation. If we wanted to use it, we would have to convert it from mass flow rate to volume flow rate. Of course, doing that is very, very easy. I hope you guys know exactly how you can do that. Okay, now that was the first thing I wanted you guys to keep in mind. The next thing, so we know to say the Q here is just the volume flow rate. The next thing that I want you guys to just know, you can highlight that. So first, this is the volume flow rate. So this is the viscosity. So of course, the symbol there is just eta. So it's a Greek symbol. And then here, this is the pressure difference, P1 minus P2. So this is the pressure difference. Next up, the R here is the inner radius of the tube. The inner radius of the tube. And then lastly, L here This is the length. So this is the length from the one that we are kind of interested in. You can say the length of the tube from the point where I'm evaluating P1 to the point where P2 is. Now, generally, this is what we're looking. This is what we're working with. This is the Poiseuille equation. The only thing that is remaining now is seeing this equation in action. One other thing that I'd like you guys to just keep in mind is this arrow here, I did specify to say this is the inner radius. So you want to look out for tricks. Some questions, especially quiz questions, they might give you something like this, and then they give you, they give you the diameter measured like that. And then, of course, this is a pipe. It can be taught to say this is a pipe. It is cylindrical, but then look at that diameter. It is measuring the outer, it is an outer diameter. So if the question is also telling you what the thickness of the tube is, or of the pipe is, then you can less the thickness so that from the diameter, so that you can get the diameter in terms of only the inner diameter. Once you get the inner diameter, half it, so that now you can get the inner radius. Okay, because it's the inner radius that we want to use in the Poiseuille equation. So I hope that is very clear, you guys. You want to look out for tricks. Look out for tricks to do with the flow rate that you're given, the units. Make sure you're dealing with the SI unit. If it's mass flow rate, make sure it comes with kgs. Time must come with seconds. Okay, if it's volume flow rate, you want to make sure that it is coming with the meter cubic, and then time also comes in seconds. But more importantly, what determines the type of units that you're going to use? Perhaps it's going to be the viscosity here, because this is the constant. So depending on what constant you're dealing with, if you wanted to use standard units where the viscosity is given some different units, you'd have to convert that viscosity to the standard units so that you can use everything correctly. All I'm saying is make sure your units are correct. So with that out of the way, we can move on to look at an example on how we can use the Poiseuille equation to calculate or to work out a problem. Okay, so this is the question that I showed you guys hopefully in the last video. So I hope you guys had time to go through it. If you haven't, you can just pause the video and try out the question. So note the values I'm using here. So here we're saying we want to use 1.0 by 10 to the power negative 3 pascals as the viscosity of water. We're given all these details about this needle and how it works, what is there, its properties, and so on. What we now want is to find the pressure difference. And remember, the pressure difference, if we go back here, P1 minus P2. So that is where the pressure difference is. So we want to find what this is. So the first step is just to get our equation. So you can start by getting, of course, the quantities that the question gives you. You can get all the information. So we have the viscosity, that is 1.0 by 10 to the power negative 3. Next up, we have the length of the needle. So this is L. This is given as 3.0 centimeters. So in meters, of course, this will come out as 0.03 meters. Next up, what else we're given? So we're being told the diameter of this needle. So the question doesn't specify whether this is an outer diameter or an inner diameter. So we're going to go right ahead and assume this is an inner diameter. So the diameter is given to us as 0.3 millimeters. So from here, we can easily get the radius. So the radius becomes 0.15 millimeters. So we convert this to meters. So this becomes, of course, you're just going to divide that by 1,000, but of course you guys already knew that. So this becomes 0.000, then 15 meters. So that is the radius in meters. Then anything else? Okay, now they want us to get the pressure difference. So the pressure difference is P1 minus P2. So you just say change in pressure. Okay. Now, how do we get this? So since we're given the viscosity, we know to say that we have to use the Poiseuille equation. So of course, the equation is, okay, I think I kind of left something. Oh yeah, towards the very end. The flow rate of water through it will be 1 gram per second. So again, notice one thing. We're just saying the flow rate. They haven't said whether this is the mass flow rate or the volume flow rate. They're just saying it is 1 gram per second. So once we look at that top part, we see to say this is a unit for mass. And once we see that, we conclude that this is actually the mass flow rate. And we know to say this is not the Q, this is J, according to the symbols that we're using. So in our equation for Poiseuille's equation, what we have is the Q, and then we have pi r to the 4. So initially we have P1 minus P2 divided by 8, the viscosity multiplying the length. So I can just rewrite this so that now I have Q is equals to pi r to the 4, where I have P1 minus P2. This is just my change in pressure, and write it like that, divided by 8, the viscosity multiplying the length of the tube. Okay, now this Q here, as we pointed out earlier, this is the volume flow rate. We want to start substituting. We want to find the change in pressure, but we just want to keep in mind that this is the volume flow rate. So if we wanted to work with this, or if we actually even try to substitute what this is supposed to be something like V over T. So this is the one that actually equates to this change in P over 8 that L. All I'm saying is this is the volume flow rate. The question gives us the mass flow rate. So we want to find a way of using this 1 gram per second that we've been given, but not as the mass flow rate. We want to use it, want to relate it to the volume flow rate. Well, the first step that we're going to do is, we say it is in grams, even though it is mass, we want to use it in kgs so that it can actually relate to everything else that we're given. So as a flow rate, it is 1 gram per second. So this is going to become 0. Or we can just even write it as 1 by 10 to the power negative 3 kgs per second. So it is now the mass flow rate, but in kgs per second. It now has the nice units. I think these units are a little bit nice. What is the J? Now, of course, if we looked at this, what you guys should recall is that from the mass flow rate, we can say density is equals to, not really from the mass flow rate, we want to change this volume flow rate so that it can relate to the mass. So we start with density. Density relates the mass to the volume in this way. So from here, this implies that mass, not really mass, I want to find an expression for the volume. So we see that volume is equals to mass over density. So now where there's volume, I'm going to substitute that 10. So not really where there's, yeah, actually where there's volume. So where there's this, I'm going to put that. So now how will it look like? Now what I have is m over this divided by t is equal to pi r 4 change in p over 8 the eta, and then we have L here. Now we simplify this expression into a single fraction, and you guys should see that what we have is m over, that is m over rho, multiplying 1 over t equal to, so the right hand side is just pi r to the 4 change in p over 8 coefficient of friction, coefficient of viscosity, sorry, multiplying L. So this, of course, reduces to be m over t rho equal to pi r to the 4 change in p over 8, the viscosity L. But I want you guys to notice this M over T. Do you see that this is just J? The mass flow rate, mass over T. So meaning this is actually, this becomes J, the mass flow rate divided by rho. This is now the one that is equal to pi R4 change in P over 8 that L. So of course, now I know how I'm going to use that mass flow rate. In other words, our conclusion here is if you're given the mass flow rate, you divide the mass flow rate by the density, what you end up with is going to be the volume flow rate. So of course, you guys can try it out. You can substitute what the mass flow rate is there and see if it's going to reduce to become that. It will. Okay. So from here, we want to make change in P the subject the formula. I'm going to cross multiply here. So now what I have is 8 multiplying the viscosity, the length, then multiplying the mass flow rate divided by pi r to the 4, the density. This is what is equal to the change in pressure. So now it's just substitution. The change in pressure is equal to the numerator, it's 8. The viscosity is given to us as 1.0 by 10 to the power negative 3, multiplying the length. It was given to us in centimeters. We converted it to meters, and we saw it was 0.03 in meters. And then lastly, we have the mass flow rate in kgs per second. So this is just, okay, so we converted it somewhere as well. Just see what we had. Okay, so we had 1 by 10 to the negative 3. So 1 by 10 to the negative 3. That was our mass flow rate. So from here now it's division. So this is pi. The radius, we know what the radius is. We did get our radius. So our radius is, it has to be to the power 4. So that is 0.00015 to the power 4. Don't forget that power. So this is multiplying the density. So this is water. So it's the density of water. We're going to take it as 1,000 kgs per meter cubic. So that's the density in kgs per meter cubic. So with that, the next thing now is just simplification of this term here. So you just want to make sure you have everything that so you have the 8, the coefficient of viscosity, then you have your length there, then you have your mass flow rate, then you have pi, multiplying the radius to the power 4, and the density of pure water. Okay, so with that in mind, simplify this. Multiplying, divide, just be very careful with your calculator. This should simplify to give you 2.4 by 10 to the power negative 7. This is supposed to be divided by 1.5904313 by 10 to the power negative 12. So if you simplify this, you end up with 1150902.4627 pascals, and lastly, this becomes 151 kilopascals. Okay, so this is the change in pressure we're looking for. I hope you guys were able to get this value. Just take note, to make this calculation, the viscosity we used was 1.0 by 10 to the power negative 3. So take note, this is the viscosity that we used for this calculation. And apart from that, everything else, literally it's exactly as is in the question. I think this is the one thing that I wanted to just point out to you guys. This is the viscosity I'm using for this calculation. So depending on the viscosity that you're using, you might be looking at a different value. Okay. Now, the next thing, in our next video, we're going to look at another interesting question. So you guys can actually try out this question. Again, when you read through, you'll notice one thing here. Somewhere along the way, they mentioned something, the viscosity. When you see this term, you already know what type of equation you must use. Okay, so with that mentioned, I'll let you guys try out this question. We'll see you guys in the next video. This was your tutor.